Alright, so now we're back. So we just talked about how the harmonic series diverges, and what we did, again, just to cover it real quickly, is we first looked at its sequence of partial sums. Then we compared a particular subset of it, the s of 2 to the n sequence, and looked at what was going on. We used a smaller sequence to show that it diverges. Therefore, the original sequence of partial sums diverges. Thus, the series itself diverges. All right. So, again, the harmonic series is that one of those great examples that you can use, especially if we talk about show that a series diverges, or use it to show that another series diverges with it. So, again, it's going to pop up in almost every single section that we cover from this point on. All right. So this is going to talk about, well, what happens if we know a series is convergent. Okay, so here is one of our first theorems that we have. So if a series, again, just writing our notation here, as I goes from 1 to infinity of a sub I, is convergent, then, and I'm going to change the notation just a little bit here, you'll see in the book that they use n instead of I, and that's, again, different authors use different types of notation, just slight variances of each other. So again, I'm going to stick with what the book typically goes with. So if the series as n goes from 1 to infinity of a sub n is convergent, again, what does it mean to converge? So let's talk about our definitions real quick of what we have. So a series is a sequence of partial sums, and the only way that it can converge is if the sequence of partial sums converges and its limit exists. If none of that happens, then the series diverges. Okay, so a lot of things has to happen with this, that the sequence of partial sums has to converge to a particular value, and we call that value S. Okay, so that's, again, a notational difference that we see here. A sub n is going to be typically reserved for series. S sub n is typically reserved for sequences. Okay, and I'm going to try to keep that notational difference with us as well, so then that way there's no backtracking on that. All right, so again, if the series is convergent, then the limit as n approaches infinity of a sub n is equal to 0. All right. So what this means is if we look at the formula of a sub n, okay, not the sequence of partial sums, but the series formula. And here I'm going to emphasize that. This is the series formula. Okay? If the series formula, if we let n approach infinity, if the series itself is convergent, then the limit of a sub n is going to be equal to 0. One thing I do want to note from this, and this is actually where we're going to get into our first test, is note the converse of this is not true. We're like, well, what does that mean? Okay, this is a one-way street. So what I'm saying here is if we said the converse is true, then we would say as if the limit of a sub n is equal to 0, then the series is convergent. This is where I'm going to go back and immediately use the previous. So, again, the converse is not true. We cannot conclude switch my letters around there. So we cannot conclude that a series converges if we already know that the limit of a sub n is equal to 0. And this is where I'm going to go back and say, okay, well, let's think about one of those. An example of this one is the harmonic series. Okay? So to briefly talk about that one, the harmonic series is the summation as n goes from 1 to infinity of 1 over n. Well, we know this diverges. However, the limit as n approaches infinity of 1 over n is equal to 0. So, that's showing that the converse is not true because we already have a proven example of a series diverging, but its limit of the series formula itself is equal to 0. So again, this is a one-way street. So again, if the series is convergent, then its limit is equal to 0. Well, this actually gives us an idea. Think about this. This is the only way that we know that a series is convergent. So a series is convergent if this happens. Well, if the limit as n approaches infinity of a sub n does not exist, or if the limit as n approaches infinity of a sub n is not equal to 0, okay, then the series is divergent. Okay, so you can just box this off just a little bit. So notice how that works. So if we find out that the limit does not exist, or it does not equal 0, then the series is divergent. Okay, so this is a really cool thing. It's a really easy test that we will be dealing with for this chapter. Okay, and it's one that we can easily check for most part. Okay, so let's just show that the series diverges. Now, one thing I do want to emphasize here, if we fail this test, so again, this is the test for divergence. If we fail this test, that does not mean that the series converges. It only converges, or the only way that we know it converges is if the sequence of partial sums exists and its limit, or converges and its limit exists. Okay, that's the only way that we know how a series converges. Okay, but if we could show that its limit of the series is not equal to 0 or does not exist, then we can say it diverges. So this only has the authority to say a series diverges. It has no authority to say a series converges. And a good case in point here, it goes back to the harmonic series, because it would fail this test because the limit does equal 0. Okay, but we know the series diverges. Okay, so looking back at this one, we're going to show that the series as n goes from 1 to infinity of n squared over 5n squared plus 4 diverges. All right, all we have to do is we look at the limit. We're going to look at the limit as n approaches infinity of a sub n. Okay, so this is n squared over 5n squared plus 4. Now, well, we see we're going to get indeterminate form, but we don't want to have to find the function that fits this, even though it's easy. It'd be x squared over 5x squared plus 4. A nice thing is we can apply a very quick algebraic technique. Okay, as n approaches infinity of 1 over 5 plus 4 over n squared. Again, divided by the largest power of n and the denominator. All right, well, as n approaches infinity, this is going to go to 0 here, this 4 over n squared, and then we're left with 1/5. Well, 1/5 does not equal 0. So here's what our write-up is going to read as. Thus, and you could be a little less formal than that, the series diverges okay, and here I want you to be very specific. So this is where we're going to be a lot more formal with our answers. And we're going to say, well, what gives us that authority to say that a series diverges? In some cases, we will talk about convergence as well. So what gives us that authority? Well, the series diverges by the test for divergence. Okay, so our solutions are going to be a lot more formal in that sense, because I want you to show why this is diverging. What gives you that authority to say that this is true? Okay. Notice here the difference between the two. If we were dealing with a sequence, Well, a sequence, as long as it approaches some value, we're okay. However, since we're dealing with a series, we need the series formula to approach 0. So notice that we're a lot more restricted on the limits here for series versus sequences. Okay? So, let's look at a couple of properties with these guys. So, if we know, so this leads into our next theorem, if the summation of a sub n as n goes from 1 to infinity, and b sub n are convergent series, okay, so this only applies if they're convergent, then so are the series c sub a sub n, okay, as n goes from 1 to infinity, the series a sub n plus b sub n, as n goes from 1 to infinity, and, oops, I left one off. So up here I'm going to redo this one. A minus b. So a sub n minus b sub n. So if we know that a sub n and b sub n are convergent, then we could talk about constant multiple is also convergent. The difference is convergent, and the sum is convergent, and we could do the following. They have these particular properties. That the series, as n goes from 1 to infinity, of c a sub n is equal to c times the summation as n goes from 1 to infinity of a sub n. Meaning this is very similar to what we dealt with limits, derivatives, and integrals. We are able to pull out the constant multiple, so this allows us to simplify things a little bit. All right. The next piece is if we do have a sum of a sub n plus b sub n, then we can split the summation up into two pieces. The summation of a sub n plus the summation of b sub n. And lastly, since we have the addition, we can have the subtraction as well. A sub n minus b sub n. This is equal to the sum, as n goes from 1 to infinity, of a sub n minus the sum, as n goes from 1 to infinity, of b sub n. Notice that this is actually applying the property A, where we have a constant multiple of a negative that we're pulling out. Okay? All right. So this leads us into a good example that I wanted to show. This one, this type of series is really cool. This is an example of a telescoping series. And we're going to see what that means here in just a second. Okay. So if we were to look at the values here, if I plugged in 1, we'd get these sets of values. 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus so on. Alright, so this is the real cool part. Let's start looking at its sequence of partial sums. So S of 1. Well, this is 1 minus 1/3. Okay? S of 2 is 1 minus 1/3 plus 1/2 minus 1/4. Notice I'm not actually going to simplify this much. But what I am going to do is I'm going to rearrange this real quickly. Because there's some real cool stuff that happens with these guys. S of 3. So we get 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5. Notice what happens. The thirds cancel each other out, leaving us with the following. 1 plus 1/2 minus 1/4 minus 1/5. Okay? S of 4. Well, this is going to leave us 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6. Well, look what happens there. The thirds cancel each other out. The fourths cancel each other out, leaving us with 1 plus 1/2 minus 1/5 minus 1/6. Okay, and in fact, if we look at the nth terms here, we get 1 plus 1/2 plus, this is where we got to look a little bit further ahead. This is our nth plus 1 term, this 1/5. And here, sorry, not plus, should be minus, so make sure that says minus. And then minus 1 over n plus 2. Well, let's look at the limit. The limit as n approaches infinity of 1 plus 1/2 minus 1 over n plus 1 minus 1 over 2, or n plus 2. Well, these both go to 0, and we're left with 1 plus 1/2. And so the sequence of partial sums is approaching 3/2. Therefore, the series is equaling 3/2. So this is the cool thing about telescoping series. We start building up this long list of numbers, and all of a sudden we see these values start canceling each other out. So think of a telescope, like old school pirate telescope, if you will. All right, those that you see on like Pirates of the Caribbean and whatnot. You've got to extend it out, and then all of a sudden you start pushing in on both ends, and what happens? It gets condensed down. And that's the really cool thing about these. All right, so that finishes up our section on series. I am going to post another video here in just a little bit of going over just a bunch of examples, but this is what a series is. So again, let's just go through the definition, and I'm going to do this at the beginning of every lecture, is talk about our basic definitions, because having an intimate knowledge of these guys is highly important. So I want you, I know it's going to get boring every single time that you hear this, but the more times that it's repeated, the more times that you're hearing it, hopefully that sinks in, because it makes it a lot easier when you're dealing with those test questions that we're going to be seeing. Okay, so what is a series? Well, a series is a sequence of partial sums. Okay, well, what does it mean for a series to converge? Well, a series converges if the sequence of partial sums converges and its limit exists. Okay, so, and it exists as a finite number. So that's what that means. And we've talked about what it means for a sequence to converge, because a sequence converges if it approaches some value. That's the only thing that we need. Okay, the next thing, well, what tests do we know? Well, we know for the test divergence is if we have the limit of a sub n, which is the series formula, if it does not exist or does not equal 0, then the series diverges. That's the only authority that it has. It does not talk about convergence. So that's the only thing that we can talk about is divergence. It does not talk about convergence. Okay, and we're going to be using that later on with this next video that I post, of going over these types of examples, dealing with geometric series and telescoping series if we see those guys. So that's the only ones that we know of. Okay, and just to reiterate what a geometric series is, a geometric series is of the form n goes from 0 to infinity of a times r to the n, or n goes from 1 to infinity of a r to the n minus 1. Those converge when, well, when do they converge? They converge when r, the absolute value of r, is between 0 and 1, diverges elsewhere. Okay, and if it does converge, it converges to a particular sum of a over 1 minus r. Now, the reason that we've emphasized the structure of those, either n starts at 0, n starts at 1, those values are the only ones that you can use provided that it matches. So if n had started at 0 and you had it to the n minus 1, you'd have to rework the problem to get it to be r to the n, not to the n minus 1. So I'm going to deal with a couple examples of those in the next video. But again, going back over your definitions, think about what a series is. What does it mean for a series to converge? What type of series do we know right now? Well, we've seen geometric series and we've seen the harmonic series. We've seen telescoping series. Telescoping series we're not really going to focus on. It's mostly just geometric. And then our very first test. Well, what does it mean for a series to diverge? What's the one test that we can use? And that's the test for divergence. So going through that list is very, very important. All right. So I'll be posting the next video in just a little bit.